We are starting chapter 5 today. Chapter 5 is all about polynomial equations. Polynomial equations. We are working both in sections 5.1 and 5.6. It's all kind of an introduction to what polynomials are, how to classify them, how to add, subtract, multiply them. 5.6 is on a theorem that deals with polynomials, but really just an introduction to polynomials today. So let's start by defining what a polynomial is. A polynomial is an expression where all exponents of variables are whole numbers. So whole numbers, no fractions, no decimals in the exponents. Whole numbers also cannot be negative. So if you have a negative exponent, it is not a polynomial. If you have an exponent of like the 1/2, it is not a polynomial. The exponent could be 0 technically. So polynomial looks something like this: 7x to the 5th minus 2x to the 4th plus 1/2 x squared minus 3x plus 7. This would be a polynomial. Notice the exponents. None of them are negative. None of them are fractions. This one here technically is x to the 0, which is okay. I have a 1/2 in there, but 1/2, that's the coefficient. That's not the exponent. So all the powers of x are positive numbers or zeros. It's like x to the 0. Standard form, the polynomial that I just wrote is written in standard form. Standard form is when we write the polynomial with decreasing powers of x. So we start with the biggest exponent and work our way down. Usually we will write our polynomials in standard form. The degree, the polynomial's degree, is the highest power of x. And last definition here, the leading coefficient. So coefficients, remember, are the numbers that come out in front: 7, -2, 1/2, -3, 7. The leading coefficient would be the first coefficient when written in standard form. So if it's not in standard form, it's not necessarily going to be the first coefficient. You either need to write it in standard form first or identify which one would come first. So it's the first coefficient, as long as it's written in standard form. That is called the leading coefficient. If I'm ever going too fast, feel free to just pause the video, rewind. We are going to classify polynomials two different ways. So classifying polynomials. We are first going to classify them by their degree, by the highest power. The degree, it could be 0. We'll come back and talk about that one. If the degree is 1, that's something like y equals 4x minus 3. X is to the first. That's the highest power of x is 1. This is called a linear equation. We talked all about linear equations back in chapter 2. If the highest power of x is 2, something like that, highest power of x is 2. That's what we did last chapter. Those are quadratics. If the degree is 3, if I have an x cubed in there and nothing higher, it's called a cubic. If our highest power of x is 4, that is called a quartic. degree of 5 is called a quintic. And anything higher than 5 does not have a special name. It's just called like a 6th degree polynomial, or 7th degree, or 10th degree. 0, it could have a degree of 0. The highest power could be 0. Y equals 7. That is a polynomial. Y is always equal to 7. No matter what x is, y is equal to 7. That's called a constant equation. So we can classify first based on degree, and then we can also classify based on the number of terms that the polynomial has. If it has one term, it is called a monomial. 2 terms is a binomial. And 3 terms is a trinomial. We've used these terms here before: binomial, trinomial. 1-term monomial, I don't think I've mentioned that before, but a 1-termed polynomial is called a monomial. Any more than that, we would say that it just has 4 terms or 7 terms or something like that. Any more than that does not have a special term. Quadnomial would seem to make sense for 4, but we don't call it that. Trinomial is as high as we go. Anything more is just called a polynomial. So let's look at an example here. It says to let f of x equal 7x squared plus 1 and g of x equal x cubed minus 2x squared plus 5x minus 3. And part A wants to know what is the degree of first f of x and then g of x. Degree, remember, is the highest power. In this case, the highest power is 2. So my degree here is 2. Highest power of x on g of x is 3. Part B wants to know the leading coefficient. For each. Leading coefficient is the number that comes out front if it's in standard form. If I look at my exponents here, x to the second, x to the 0, they do start with the biggest and go down. The leading coefficient is 7 for f of x. G of x, this is my degree. Leading coefficient is 1. Part C asks us to classify each f of x and g of x based on degree and number of terms. For each f of x and g of x. F of x, the highest power of x was 2, so it is a quadratic. And it has 1, 2 terms, so it is a binomial. G of x had a degree of 3, so it is cubic. And it has 1, 2, 3, 4 terms. 4 does not have a special name, so it's just a cubic polynomial. f of x is also a polynomial. It's just a special type of polynomial called the binomial. Part D asks us to evaluate f of x minus g of x. F of x minus g of x. So we are going to take f of x, 7x squared plus 1, and I want to subtract g of x, which is x cubed minus 2x squared plus 5x minus 3. To subtract here, we do not FOIL. It is important to put this in parentheses because you are going to need to distribute this minus sign. So I've got 7x squared plus 1, then I need to subtract this whole thing. So I'm subtracting x cubed. I'm subtracting negative 2x squared, minus minus is plus, minus 5x, minus negative 3. It doesn't say it here, but we need to write our answer in standard form. So we're going to combine like terms and write in standard form. So I've got this negative x cubed. That's my only x cubed. I've got 7x squared plus 2 more, makes a total of 9x squared. I've got this minus 5x right here. And I've got plus 1 plus 3, which is plus 4. One more part to this problem, part E, asks us to evaluate f of x times g of x. This one we were subtracting, now we're multiplying f of x and g of x. So we're taking f of x, 7x squared plus 1, and we are multiplying it times g of x. When this was a binomial times a binomial, that's when you learned how to FOIL. First, outside, inside, last. We kind of do this the same way, but it's a little bigger than the normal FOIL. So what you're going to do is you're going to take the first term and multiply it by each of these terms. So 7x squared times x cubed. So I've got 7. X squared times x cubed, when you multiply, you add the exponents, 2 plus 3. So that gives me 7x to the 5th. 7x squared times negative 2x squared. 7 times negative 2. X squared times x squared, we add the exponents. 7x squared times 5x. 7x squared times negative 3. I've multiplied the 7x squared times each of these terms. Now I move over to the next one, which is 1. So 1 times x cubed. 1 times negative 2x squared. 1 times 5x. 1 times negative 3. A good way to check to make sure you've done everything you need to do here before you combine up like terms. This has 2 terms. This has 4 terms. 2 times 4. You should have 8 terms before you combine them up. 1, 2, 3, 4, 5, 6, 7, 8. So we know we did everything that we needed to do. Combine like terms and write in standard form. 7x to the 5th minus 14x to the 4th. Got 35 plus 1 more. I've got 36x cubes. Minus 21 minus 2 is minus 23x squared. Plus 5x minus 3. Example 2. Example 2 gives us a table here. It asks us to find a cubic function that models this data set, and then use the function to estimate the average monthly Social Security benefit for a retired worker in 2005. It does tell us to use the number of years past 1940 for X. So 1940, X would be 0. The 1950 is 10 years past 1940, and so on. We enter our data the same way we did with linear regressions and quadratic regressions. We go to Stat, Edit. If you have any data in there already, clear it out. Our X's are going under list 1. And our Social Security benefits are going under list 2. It asks us to find a cubic model. We want a cubic regression equation. We go to Stat, Calculate. We've done linear regression, which is number 4. We've done quadratic regression, which is number 5. Notice if we want a cubic, you're going to number 6. Quartic, that's 4th degree, that's number 7. Doesn't do anything higher than that as far as polynomials go. So my X's are in list 1, my Y's are in list 2. I am going to store my regression equation under Y1. Alpha trace Y1 and calculate. So the equation that we're looking for is Y equals, be careful here, this is not 2.04x cubed. This e negative 4 means times 10 to the negative 4th. So I need to move the decimal point 4 times. This is 0.0002 x cubed plus 0.262 x squared minus 3.624 x plus 29.305. So there's the cubic function. Could zoom number 9 once our plot is on. Does not appear as though it is. So I'm going to turn my plot on. Now zoom number 9. We should be able to see the data as well as our curve that comes pretty darn close to most of the points there. To answer the question, what the average monthly income would be in 2005, that is 65 years past 1940. We want to plug in 65 for X. If you're going to just plug it into the equation, you want to write down more decimals than just 3 here. I would probably write down most, if not all, of the decimals that we get right here. Or another way you could do it is to look at your table. So second graph pulls up my table. I want X to be 65. You could push down 65 times, or I guess 63 times for me here. Or it says press plus for delta table. If I push plus, it's only giving me the opportunity to change my delta table. So you could make this something so that it'll jump up to 65, or probably even a better way. Let's go ahead, let's look at our table set. Second window will set up my table. Wants to know where do I want to start my table and how much do I want to change it by. So I want my table to start at 65. So that 65 is right on there. Now when I go to table, second graph, now notice the first value is 65. that beats pushing down a whole bunch of times. Notice my y value, which is what I'm looking for, is $955.82. And one more thing we need to look at, everything that we've done so far is in 5.1. This is officially 5.6. 5.6 has lots of theorems in it, but the one that we need to know is called the fundamental theorem of algebra. The fundamental theorem of algebra. And it says, including duplicate solutions, an nth degree polynomial has n complex solutions. As long as we include duplicates, an nth degree polynomial has n complex solutions. So if I have a cubic equation, this has 3 solutions. If I have a 4th degree polynomial, this has 4 solutions. Now it does say complex solutions, so some of the solutions might be imaginary. Like this one here only has 1 real solution, but then it also has 2 imaginary solutions that we'll talk about how to get eventually. This one here has 4 solutions. Some of them might be real, some of them might be imaginary. When it says including duplicate solutions, sometimes some can occur twice. So like if we have x squared minus 6x plus 9 equals 0, and we wanted to solve this, we would say x minus 3 times x minus 3 is 0. So we get x is 3, and then I get x is 3 again over here, right? So technically there's only one solution. X equals 3 is the only solution. This is saying including the duplicates one though. So we're going to count this as 2 even though they happen to be the same thing. So the degree is 2 and I wind up with 2 solutions. Last example, example 3, says how many complex solutions does h of x have? And we are given h of x is 9x to the 7th plus 2x to the 4th minus 3x to the 12th plus 4x squared minus 3. I guess it asks for solutions. How many complex solutions does the equation have? So including duplicate solutions and including imaginary solutions, the number of solutions is equal to the degree. The degree, the highest power of x, is 12. So there are 12 complex solutions. That's all there is to it. Didn't ask us to find them, thankfully. We just need to state how many there are. The last page of your homework, in the directions, it says just state number of solutions. So that's all you're doing on that last set. You're not finding the solutions. You're just stating how many of them there are. That is an introduction to polynomials, sections 5.1 and 5.6.